All right, today we're going to crack open a technique that can feel like a secret weapon in coding interviews, the two-pointer method. We're going to break down the key patterns that turn slow, clunky code into these elegant, super efficient solutions. Let's dive right in.
You've been there, right? We all have. You write a solution, you know it works logically, but then it just times out. You know the one I'm talking about, that dreaded O of n squared complexity that comes from those nasty nested loops? It's a classic roadblock. But what if there was a way to basically collapse those loops into a single, clean pass?
Well, that's exactly where the two-pointer technique comes in. It's a family of strategies that use two coordinated pointers, which are really just indices or iterators, to scan through your data. And the real magic is in how they move together. They follow these specific rules to just chop away all the redundant checks and get you to that beautiful, coveted linear time complexity.
Okay, so let's get to the real heart of it, the speed boost. The entire goal of this technique is to hit an O of n runtime. And what that means is we process our data in a single pass. This is a huge performance gain that can take your solution from timing out to passing instantly. The easiest way to wrap your head around this is with a simple analogy. Just imagine you have two markers on a number line. Now, instead of checking every single possible combination, you just move these markers in a coordinated, intelligent way to zero in on the answer. It's that coordinated movement that's the absolute key.
Okay, let's make this real with our first core pattern. This is probably the most common and, honestly, the most intuitive one you're going to see, the opposite ends pattern. So, picture this classic problem. You're given a sorted array of numbers and some target value, and your job is to find two numbers in that array that add up exactly to that target. Now, the brute force way is a nested loop, right? O of n squared. But because the array is sorted, we can do so much better.
So here's how it works in action. We start one pointer, let's call it L, at the very beginning, and another one, R, at the very end. We add up their values. Now, if that sum is too small, what do we need? A bigger number. And since the array is sorted, the only way to guarantee a larger sum is to move our left pointer, L, to the right. And if the sum is too big, well, we do the opposite. We move the right pointer, R, to the left. With every single step, we are intelligently narrowing the search space, just closing in until we either find our target or the pointers cross.
And the result of this whole elegant dance? A beautiful O of n runtime. Each pointer only moves across the array once. No nested loops, just one single efficient pass. That is a total game changer. All right, pattern number 2 is a wonderfully versatile one called the sliding window. This is going to be your best friend for any problems that involve subarrays or substrings that need to satisfy some kind of condition.
Seriously, a great way to picture this is to think of a rubber band stretched over a part of your data. You can expand this window by moving the right end, and you can shrink it by moving the left end. This dynamic, expand and contract mechanic, that's the heart and soul of this entire pattern. So here's the core loop, the secret sauce, right? You just keep expanding the window by moving your right pointer forward. And with each little expansion, you ask yourself, is my window still valid? Maybe the rule is no repeating characters, or at most k distinct elements. The very second your window becomes invalid, you start shrinking it from the left until it's valid again. And all the while, you're keeping track of the best, most valid window you've seen so far.
And trust me, you see this pattern everywhere in coding interviews. Problems like finding the longest substring that has unique characters, or maybe the shortest substring that contains a certain set of characters, these are all classic sliding window problems.
Okay, our third pattern takes us out of the world of simple arrays and strings and into the world of linked lists. This is the fast and slow pointer pattern, and it is an incredibly clever application of this whole two-pointer idea.
I want you to imagine two runners on a track. One moves at a normal speed, that's our slow pointer. The other one moves twice as fast, that's our fast pointer. Now, if it's a straight track, the fast runner just gets to the end first, no big deal. But what if there's a loop in the track? Eventually, inevitably, the fast runner is going to come all the way around from behind and lap the slow one. That collision, that moment they meet, that's the key to how we know there's a cycle.
This tortoise and hare approach has two primary and very powerful applications. The first, like we just said, is detecting if a linked list has a cycle. But the second one is for finding the middle node of a list. Think about it. When the fast pointer, moving twice as fast, reaches the very end of the list, where do you think the slow pointer is going to be? Exactly in the middle. It's brilliant, really.
And hey, this isn't some newfangled trick we just came up with. This is a classic algorithm, often called Floyd's cycle-finding algorithm, and it dates all the way back to 1967. It's really a testament to how fundamental and powerful these ideas are in computer science.
So, we've gone through the 3 big families of two-pointer patterns. Now, let's bundle all this up into an actionable toolkit that you can take with you into your next interview.
So, a really common question you might get is when to use two-pointers versus, say, another common tool like a hash map. Well, the crucial difference often boils down to space complexity. As you can see on the left, the two-pointer technique usually works in place, which means it doesn't need extra memory as your input gets bigger. That's O of 1, or constant space. A hash map, on the other hand, needs to actually store elements, so its memory usage grows right along with the input, giving it O of n space. Being able to explain that trade-off is a huge plus in any interview.
Look, mastering these patterns is a journey, and this slide, this is basically your roadmap. You start with those fundamental building blocks we've been talking about, like opposite ends for pair sum and the fast and slow pointers. Then from there, you build up to more complex variations, like three-sum, more advanced sliding windows, array partitioning, and even the famous container with most water problem. Every single one you practice just adds another powerful tool to your problem-solving toolkit.
And finally, let's talk some real pro tips for when you're actually in the interview. First, always communicate your approach before you even start to code. State the invariant. That's the core rule your pointers are going to follow. Second, think about the mechanics. Always clarify if you can modify the input, like by sorting it, and be super methodical about edge cases like duplicates. And third, analyze your logic. Be ready to explain why your pointer movements are guaranteed to be correct. This shows a way deeper level of understanding than just being able to write the code.
And there you have it. The two-pointer technique is so much more than just a clever trick. It's a fundamental way of thinking about how to process data efficiently. By recognizing these patterns, opposite ends, sliding window, and fast and slow, you can transform really difficult problems into simple, linear time solutions. The only question left is, which one are you going to master first?